Hello everyone, my name is REDJEB Youcef. I am a PhD student at the National Polytechnic School of Constantine in Algeria. I have the pleasure to be here with you today. Today, I'm going to present our work under the title Evaluation of a Steam Ranking Cycle for Waste Heat Recovery from Preheater Tower in a Cement Industry, which is under the supervision of Professor Jarafi in collaboration with Professor Ernesto Pato and Alberto Benato. So, this presentation is outlined as the following plan. I'm going to start with a short introduction. Next, I will give an idea about the problematic and the objective of work, moving to the concept of waste heat recovery at the level of cement industries, which will be followed by the steps involved and followed for our study, and finally, the optimizer stinks and results. Introduction. As it is known, the cement manufacturing process is a highly energetic intensive process because of the use of high temperature degrees at the level of the different plants, which results in a real significant loss of the heat. So, according to that, we focused our work on waste heat recovery and the power generation using waste heat at the level of cement industries in order to reduce energy consumption and greenhouse gas emissions. As what I have said before, the production of clinker results in a large loss of the heat, in particular at the level of the preheater tower in the form of the exhaust gas, with a temperature can achieve 400 degrees Celsius and a significant flow rate, and also at the level of the cooler in the form of hot air, with the temperature can achieve 250 degrees Celsius. For that, the objective of our work is to evaluate the possibility of recovering the waste heat at the level of the cement industries, in particular Algeria, in order to reduce the consumption and as a means to reduce greenhouse gas emissions and to cover a part of electricity consumption in case of electricity generation. For this purpose, we can categorize three methods of waste heat recovery that probably can be applied at the level of the cement industries. The first one refers to the capture and transfer using heat exchangers, where the heat can be utilized for heating the building during the winter period, for example. The second one refers to reintegration, means the reuse of the heat source at the same installation, for example, in order to preheat the raw materials, which can lead to a higher production rate with the same consumption. And finally, the generation of electricity by using the different known technologies such as steam Rankine cycle, organic Rankine cycle, and air bottoming cycles. And this third method is the main method that we are focusing on in our project. The main thing in this work is to study the possibility of recovering the waste heat in order to generate electricity using steam Rankine cycles. The study of this technology is done using different softwares besides the MATLAB by developing a code integrated with those softwares, in particular REDJEB, in order to calculate the different parameters and thermodynamic points of each technology. Description of the technology. The operating principle of this technology consists in pressurizing the fluid in a pump, then it flows into an evaporator where its state changes to a vapor. Next, it enters a turbine as a means to generate electricity, then it leaves the turbine as a vapor at low pressure, and it flows throughout a condenser where its state changes to a liquid again, and finally the cycle starts again. Range of application: low and medium temperature. Advantages: low risk and environmental friendly fluid. There is no need of intermediate loop. Disadvantages: maintenance and corrosion, humidity at the outlet of the steam turbine which influence on its blades, leading to lower life, and medium efficiency. Steps involved in our study. In this study, the first thing that we did is the estimation of the quantity of the waste heat or availability of the heat at the level of the cement industry, then fixing the different parameters, and finally the simulation and the results. So, to do that, we select a case study presenting a cement industry in the north of Algeria, Hamabouzayan, and we determine the necessary data and parameters. Then, using MATLAB software, a development of a code was done in order to carry out the thermodynamic optimization of the desired technology. MATLAB software, of course, is linked with the REDJEB database as a means to calculate the thermodynamic parameters and finally get the results and the plots. The developed code in MATLAB consists of the following steps. Employ the genetic algorithm beside the database of REDJEB software in order to calculate the different thermodynamic parameters and points. Then, the computation of the different input parameters. Next, optimize the net power output, and finally return results and the optimum parameters are optimized. In the part which depends to the thermodynamic optimization, the code should optimize the net power output and estimate the different efficiencies, such as the cycle efficiency, then calculate the different optimum parameters. Then for the economic analysis, the code should determine the price of the technology using the different equations and correlations adopted from the literature, and the payback time and the net present value. In this work, the design and the optimization of the SEAM21 cycle are performed using a single objective function, aiming to maximize the net power output. For this purpose, the basic architecture is implemented in the code. The selection of this configuration was in the aim to reduce the planned costs and complexity. For this SEAM21 cycle, in this case, we used the exhaust gas directly without the need of a thermal loop, as water is an environmental friendly fluid and it's not flammable. The main heat exchanger in this case also is assumed to be of the shell and tube type. This type is selected as it is suitable in case where we have a large difference in the pressure of the fluids in exchange and also in their heat transfer coefficients. The main heat exchanger is a collection of three parts, namely economizer, evaporator, then a superheater. The different parameters of the different devices of the cycle were chosen according to the literature and plant manufacturer data and knowledge. Then, the upper and lower boundaries for the different variables are selected and assigned based on the author's experience and the literature. A thermodynamic optimization aiming for maximizing the net power output is carried out using the developed code, which employs a single objective function where the selected different parameters are a number of generation 200, populations 150, crossover fraction 0.8 and mutation fraction 0.2. So the optimization results of the SEAM21 cycle technology show that the use of this technology for waste heat recovery at the level of preheater tower of the cement industry guarantees a net power output can achieve 1.87 megawatt with an optimum evaporation pressure of 17.95 bar, condensation pressure of 0.14 bar, and the quality of vapor of 0.99 as shown in the table. On the other side, the thermal efficiency of the cycle is 21.64%. These results prove that the implementation of the SEAM21 cycle as a way to recover the waste heat at the level of the Algerian cement industries can be useful. The cycle representation in TS diagram and the pinch point in the evaporator in TQ diagram are depicted in the following figures. Then, for the economic analysis, the results show that the SEAM21 cycle technology guarantees a net present value of $7.06 million with a payback time of 8.5 years. These can be acceptable in a lifetime of the cycle supposed to be 25 years. These, the thermodynamic optimization and the economic analysis exhibit that the implementation of SEAM21 cycle technology for this application guarantees good thermodynamic performance besides the acceptable economic results. So, as a conclusion, we can say that these obtained results mention that the implementation of SEAM21 cycle at the level of the preheater tower of this industry can cover around 12% of the total electricity consumption in the industry. At the same time, the cycle can produce around 44 megawatt a day. This quantity of power can cover around 70% of the industry need of electricity during the rush hours, as the average of consumption is around 15.4 megawatt hour. Which leads to the reduction of the electricity bills with around 40%. Any questions? Thank you for your attention.